All right. So in this video tutorial, we are going to be talking about circular motion. So we first need to talk about the path of the object and how at a given point you've got a velocity, and at another point you've got another velocity, and we're going to talk about uniform circular motion. So in other words, these two velocities are equivalent. Now, since the velocity is changing direction, you must have acceleration. This acceleration is always directed towards the center of the circle, or it's directed radially. Now, how to find this acceleration? We looked at how your radial acceleration is equal to v squared over r, which is the radius of your circle. Now, we related the velocity to the distance over time. Well, distance is 2 pi r for the radius of a circle. And time we called capital T. That stands for the period, or the time it takes for one revolution. So this also equals, well, now v is 2 pi r over t squared, so this becomes 4 pi squared r squared over t squared r. So we see that one of our r's cancels, and we are left with 4 pi squared r over t. So that relates our radial acceleration to our period. Now, we know from Newton's second law that if we have a net acceleration, then there must be a net force. Well, that force is also directed in the same direction as your acceleration. And so in class we did an example with the Ferris wheel, and we had a big old circle, and we talked about the weight of the object doesn't change. But what does change is the normal force. So up top, up here, my net acceleration is directed down. So in other words, the net force in the y direction, because we're dealing with straight up or straight down, equals, again, my mass times acceleration. Well, in that case, it's my mass times my a radial acceleration. And that radial acceleration equals, if we take the up to be positive and the down to be negative, well, then I've got Fn minus mg. Well, I must have a negative acceleration because my acceleration is directed down. It's directed this way. So, in other words, this weight needs to be greater than my normal force. So we talked about how at the top of the Ferris wheel you have a smaller normal force than at the bottom, where you have a greater normal force than your weight. That's why at the top of the Ferris wheel you feel that woo feeling, because we are feeling our normal force. And that's why at the bottom of, say you're going into a roller coaster loop, whenever you go up, you feel that force pushing you down, or you're sinking into your seat. That's because your normal force is increasing. So, a good type of problem with this is the car on a banked curve type problem, or car on a curve problem. And so if we're thinking about a car, this is a very boxy car, and it is going in a circle, say its path is like this. Well, it has its weight, or the force due to gravity. It's got its normal force, and the net acceleration is directed towards the center. Well, the net force is going to be the static friction between the road and the tires. So I have no acceleration in the y direction. I'm only accelerating in the x direction. So the force due to static friction is again your mu s times your normal force. Well, in this case, since I have no net y acceleration, that means that my normal force minus my force due to gravity must be 0, because the sum of the forces in the y direction must be 0 if I have no acceleration. So that means that my normal force equals the force due to gravity. So I could use this to find the force due to friction. If I knew the radius of the circle, I could la 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 la. So let's do an example with that. Let's look at a car that is moving or turning on a flat road, and let's say the car weighs, let's say we've got a Yaris. It only weighs about 500 kilos. I'm kidding, I don't really know. And the maximum, or let's say the coefficient of static friction for, let's say we're on an icy road, so it's 0.2. And let's say the radius of my turn is, well, let's say 10 meters. Okay. And I want to know what is the max speed I can take that turn with this coefficient of static friction. So again, we do our free body diagram. I've got the force due to gravity, and I've got my normal force, and I've got my force due to static friction. So my normal force is going to be equal to the force due to gravity. So I've got Fn equals mg, and the maximum static friction that can be applied is 0.2 times mg. So if I go 0.2 times my mass, which is 500, and let's go 9.8 for gravity. So the maximum static friction that I can apply is 980 newtons. Okay? Now, my net force, summation of forces in the x direction, equals my mass times my radial acceleration. Now, I'm wanting to know the max velocity that I can take. So I'm going to go mass times my v squared over r. I don't know my velocity. I know my mass and I know my radius. And I know that that has to equal the net force, which is my static friction force. So that is going to equal 980. So I can use this and solve for v squared. So if I divide by m, divide that by 500, and then multiply that by my radius, I get v squared equals 19.6. Well, if I take the square root of that, I get my max velocity would be 4.42 meters per second. Okay? So, that is a way that you could use to use the information that you're given and find the max speed for your turn. You could also find the minimum radius, the maximum radius, stuff like that. Not maximum radius, excuse me, minimum radius. Maximum radius could probably be as big as you want. So that is a turn that's on a flat road. So this type of problem also works with say you're given a problem where you've got a turntable, like that green thing that I've got in the room. And let's say it's spinning this way. And let's say I've got a little spider on here. You know that spiders have 8 legs, but I can only fit, well, I take that back, I can fit 8. There we go. So, it's spinning this way, and let's say it's spinning at a uniform velocity. So, the acceleration that spider experiences is right there. That means that the frictional force that spider experiences is also directed towards the center. Now, if it's not high enough, that spider will skid out, tangent to his path. So, it's important to know where the force is directed and where the acceleration is directed. They're both directed the same way. So, that is circular motion. And this will be part 1. The next part, we will talk about turns on a banked road.